In using Gauss-Jordan Elimination Method in getting the solution of a linear system, we have to transform the given linear system to its augmented matrix. For the benefit of others, in having augmented matrix, we have to get the coefficients of the given linear system and its corresponding constants. If the goal of back substitution method or Gaussian elimination is to have a row echelon form, what the Gauss-Jordan elimination method wants is to have a reduced row echelon form. That is, it has to have this form. Once we obtain a leading one for a given row, the rest of the entries in the column containing that leading one should be 0. So having this as a leading one for the second row, the rest of the entries in this column or the second column must be zeros. Similarly, we have this. Observe that if we have this form, it's easy for us to identify the values for our given variables. In this case, knowing that the first column would be for the variable x sub 1, the second column would be x sub 2, third would be x sub 3, and fourth would be x sub 4. It's easy for us to transform this back to the given linear system and have the corresponding values for the given variables. The algorithm in producing reduced row echelon form is sort of like the same with the row echelon form. And so if you want to know about these steps, it's preferable to watch first the back substitution method or the Gaussian elimination method. Everything is discussed there on how to make use of the elementary row operations. The difference between reduced row echelon form and row echelon form is that in row echelon form, it just needs the leading ones per row. But as for reduced row echelon form, it needs the rest of the entries in the column that contains leading one to be zeros. Hence, the 4 here must be 0. Since we now have a pivot point here, which is 1, let's just multiply that to a negative 4 and add that to that 4 so that that 4 will be 0. That is, we now have negative 4 times the second row plus the first row. In case you're having confusions on how to make use of the elementary row operations here, it's preferable to watch that back substitution method or Gaussian elimination method first. Our second column now has just the leading one, and the rest of the entries in that column are zeros. Thus, we can now proceed to the third column and have 1 as a leading one in the third row, and have the rest of the entries in that third column to be 0. And yes, to make 3 to be a positive 1, we just have to multiply that by a 1/3. This time, we have to make these entries zeros. Hence, we have to multiply the third row by a negative 2 and add that to the second row. Similarly, we just have to add the third row and the first row to have that 0 there. Now we have a reduced row echelon form. Take note that in producing reduced row echelon form, we have to produce a leading one first before we can make the rest of the entries in that column to be zeros. Then we can move to the next column. Therefore, the solution for this linear system would be a point negative 1, 1, 1. For the benefit of others, if this becomes 8, the value for x would also be 8, and this value for y would now be 10. This is based on the idea of transforming an augmented matrix back to its linear system form. And yes, aside from checking the obtained answer through calculations, we can definitely graph this and check if the solution would really be the intersection of this given linear system. hope you can solve this using Gauss-Jordan Elimination Method. And yes, it's possible for us to have fractions, okay?